Alright, so this is our last problem that we're going to be looking at. And you might say, oh, nothing, no parts A, B, C, D, and E and all that other nonsense and whatnot. Oh, this is going to be easy. Well, yeah, you might want to think that, but actually our little tick marks here is telling us that it's a level 4. Might indicate otherwise. Let's go ahead and read through this. It says the 2 kilogram, 30 centimeter diameter disc in this figure right over here is spinning at 300 RPMs. How much friction force must the brake apply to the rim to bring the disc to a halt in 3 seconds? And so when this brake, we'll assume it applies, it hits there right at that point. That would obviously apply a torque in the opposite direction, a torque pushing downward, which would then cause a negative acceleration and therefore is going to cause that angular velocity to decrease all the way until 0. So, it's going to start off, this wheel's moving round and round and round, but then as that brake applies, it's going to start slowing it down, and eventually it'll come to a complete stop. So, let's underline some of this important information and figure out what's going on. Well, we've got the mass there, 2 kilograms. Diameter is 0.3 meters, which means the radius is 0.15 meters. And 3 seconds is our time. Our initial velocity, angular velocity that is 300 revolutions per minute. And we're going to very quickly convert that into radians per second. So multiply by minutes over seconds to get rid of the minutes, and then times radians over revolutions to cancel out those revolutions. And we end up with an initial angular velocity of 31.4 radians per second. Time of 3 seconds. This is going to bring it to a halt, which means that our final velocity, final angular velocity rather, omega, is 0 radians per second. All sorts of hidden information in there. Lots of good stuff for us to work with. So you may notice, whoa, I've kind of been dealing with some problems with this before. Omega naught and T and omega. There's a formula I've been dealing with that's been sort of affecting those, and in fact we're going to use that formula yet again. Omega, final angular velocity, equals omega naught plus alpha t. We know 3 of those 4 things. So what we'll do is we'll solve for alpha, which is the angular acceleration that's going to be causing it to have angular acceleration in the opposite direction of that omega. So when you plug in those numbers, 0 minus 31.4 divided by the time, you end up with about approximately 10.47 radians per second squared. So we've got an alpha, and we need to work our way down to the force that is applied. Since the question is, what is the friction force that this applies? In other words, which friction force means this is going to cause friction. So what is that force? Some of the things that we've got to take into consideration is that there's going to be some sort of torque when we apply a force at a distance from the pivot point. That's going to be causing a torque. There's also going, since this disk wants to continue to rotate, then it's going to have a moment of inertia. So we're going to have to take that into consideration. In other words, it wants to continue to spinning. You just apply a brake and just touch it, it's not going to stop all of a sudden. So we'll write down some formulas that are going to relate these different concepts together. First off, the torque is equal to Fr sine theta. That's just sort of the go-to definition we had for torque. That angle, theta, is going to be 90 degrees, so that's nice. This term turns into 1. So the torque that is applied to the brake is the force times the radius. And we know the radius, that's 0.15. So that's great. We don't know the torque, but we don't know the force, we do know the radius. So we know one of those 2 things. But then there was another concept here, the moment of inertia. And we have a formula for that. Torque equals I alpha, or this is just a slight variation on the formula. Alpha equals torque divided by moment of inertia. So if you just manipulate that slightly, you get this. So what we're going to do now is we're going to say, well, all right, well, this torque, it must equal that torque. Those things are the same. So therefore, F times R must equal I times alpha. If we divide both sides by R, we end up with I alpha over R is equal to our force. So Since this is a disk, we're going to use the formula from the textbook, 1/2 mr squared for disks, for the moment of inertia, times the alpha, which we obtained a little bit earlier, divided by the radius, and we end up with an answer of 1.57 newtons. That's the force that will be required in order to affect an angular acceleration, which will slow this down to 0. So thanks for watching. I hope you enjoyed it.